Our objectives in this lesson is to be able to use the Pythagorean theorem to find the lengths of sides of right triangles and use the Pythagorean converse to classify triangles as acute, obtuse, or right. Recall the Pythagorean theorem. This is used to solve for the length of unknown sides in a right triangle. While you'll usually see the equation for the Pythagorean theorem written in alphabetical order, we're going to write it as c squared equals a squared plus b squared because it is usually more useful that way. Remember that the hypotenuse is the longest side across from the right angle. So in a right triangle, we find the right angle, look across from the right angle, not the sides touching, but the side that is not touching the right angle, and represent that side with the letter C. The other two sides, the legs, A and B, can be either of the legs because we're adding, that part doesn't matter. Let's look at examples to talk about how to solve using the Pythagorean theorem. In this problem, we see a right triangle where we know the side lengths, but we're missing this side length. Remember, Pythagorean theorem is used to solve for the unknown side when we have the other sides in a right triangle. So I start by finding my right angle. I look across the triangle from the right angle. Sometimes we can think of using this little right angle mark like its own arrow pointing across the triangle. This is the longest side, which is across from the right angle, so this side is our C. We know that we're finding a missing side of a right triangle, so we start by writing our Pythagorean theorem equation, c squared equals a squared plus b squared. We've identified our c, so now we can substitute x for c. X squared equals, the other two sides are the legs. It doesn't matter the order because they're added after they're squared. And then we will simplify this side with the numbers. 12 squared is 144, plus 16 squared is 256. Adding them together makes 400. And then finally, we want to make the squared go away, so the inverse process is taking the square root. Using our calculator, if we need to, the square root of 400 is 20, so x equals 20, and that's the missing side. Let's look at the second example. There is a zip line from the top of a tree to a spot that is 20 feet away. If the zip line is 52 feet long, how tall is the tree? Notice I underlined some of the key information in this problem. I'd like to do a rough sketch of what is happening here. A tree is usually standing straight up and down, so I'm going to draw the tree vertically. Then we have a spot that's 20 feet away from the tree. So that would be along the ground, 20 feet. Usually anything that's vertical and anything that's horizontal can be assumed to be making a right angle or be perpendicular. So I'm going to draw that. The zip line goes from the top of the tree here to the spot 20 feet away here. So that's going to connect those points. And the zip line is 52 feet long, so I'm going to label the zip line 52 feet. The question is, how tall is the tree? That's the length I don't know. I'm going to label it x because that's what I don't know, but I want to find. Because these are sides of a right triangle, I will use the Pythagorean theorem. I start by writing the equation c squared equals a squared plus b squared, and I identify my c. I see the right angle, I use it as an arrow to point across the triangle to that longest side, 52 feet. So 52 is the C. We can leave the units out of the equation when we're writing it in. 52 squared equals, and the other two sides can go in any position remaining. X squared plus 20 squared works out well. 52 squared is 2,704. And 20 squared is 400. We'll solve this equation by subtracting 400 from both sides, which gives us 2,304 equals x squared. And finally, we need to take the square root to get the squared to go away, and we get that x equals 48. That's not our final answer because this is a problem that has words and units of measure, so we answer our problem with words or units of measure. The tree is 48 feet tall, and that's our answer. Let's look at this example. Solve for x. So I see where x is, and it is involved in this right triangle here. It is a side of the right triangle. So I'd love to use my Pythagorean theorem to find that missing side. But notice that I only know this other side. I don't know this leg. Let's take a look at the other right triangle that's attached to it. I'm going to bring over something to cover up that first right triangle. Now notice that because these triangles are attached, I can find this missing side of the right triangle by using this triangle that does give me two side lengths. So let's use the Pythagorean theorem to find that missing side. C squared equals A squared plus B squared. Let's identify our C in this right triangle over here. So across from the right angle, using it as an arrow, it's pointing to this side right here. That's our C. So 25 squared equals, this one doesn't have a label, we can simply call it A. A squared is that missing side, plus 24 squared. Let's simplify these squares. 25 squared is 625, and 24 squared is 576. Getting A by itself, we subtract 576 from both sides and get 49 equals A squared. Of course, we know we need to take the square root of both sides to get A by itself, and 7 equals A. So now we know this missing side is 7. Let's remove the cover up so that we can see the other triangle clearly now. Now we know we need to find the x, and now we have that missing side is 7. So using, again, the Pythagorean theorem, writing our equation c squared equals a squared plus b squared, let's identify our c from this triangle. Here's the right angle. It points to this side. This is our c, the x. Substituting into the equation, we get x squared equals, and then I've got the other two sides of this right triangle, the 7 and the square root 26. So 7 squared plus square root 26 squared. X squared equals 7 squared is 49, and square root 26 squared is just 26. The square and the square root are inverse processes of each other. They cancel each other out. So just 26. If you're unsure about that, you can always type that in the calculator and see for yourself. Adding those numbers, we get x squared equals 75, and of course we take the square root to get the squared to go away. Let's practice simplifying this radical, because if I type in square root 75 to my calculator, it doesn't give me an exact answer. X on this side, and I can think of a perfect square that goes into 75. That's 25. Thinking of money, quarters, 75 cents is 3 quarters. 25 cents times 3. I can write this as square root 25 times square root 3. And because 25 is a perfect square, I can take the square root of 25, which is 5. So my final answer is 5 square roots of 3. If I needed a decimal answer, I would type that into my calculator and get that x is approximately 8.66. Another valid answer, this one being exact and this one being approximate. Notice that when I type them both into my calculator, square root of 75, it gives me 8.66, and 5 square roots of 3 gives me 8.66. They are equivalent. It's just that this is the simplified radical. Let's take a look at one more example. Find the length of the diagonal of the square. The diagonal of the square is shown as this line segment right here. That's what we're looking for, but we don't know, so we'll call that side x. Now I notice that while I do have a square, because there's the diagonal, the square is divided into two triangles. If I just focus on this right triangle here, I know that because I have these two sides, I can use the Pythagorean theorem to solve for that missing value x. So we'll write c squared equals a squared plus b squared. We use our right angle to identify where the c is. X is c. So x squared equals 5 squared plus 5 squared. Let's simplify on the right side. 5 squared is 25, so 25 plus 25. Adding those together makes 50, and of course we need to take the square root. Just x over here, and 50 has a perfect square in it. It is not a perfect square itself, so it will give us a decimal value, just like in the previous example. I know that 25 goes into 50, so I can write square root of 50 as square root of 25 times square root of 2. Square root of 25 is 5, with square root of 2 left over. This is an excellent answer. This is a simplified exact answer, and if I type it in my calculator, I get that x is approximately 7.07 or 7.1, depending on how we want to round. Thanks for watching.